Hello gentlemen, welcome to section 7 on impulse and changes in momentum. Here we're going to be studying crumple zones. So first let's talk about what that will recognize that forces affect collisions. So in an effort to make a collision softer, in class right now we're examining the crumple zones of our homemade paper cars. And we're discovering that larger crumple zones equal softer collisions. It was softer. We don't really use that term in physics, but right now we can. And based on the work kinetic energy theorem that we've learned, we know that work is equal to the force times the distance, which equals a change in kinetic energy. So work is equal to a change in kinetic energy. So the crumple zones, as the airbags in a car, are in place to decrease the force by increasing the distance over which this force is acting. The work done on the car then reduces the kinetic energy of the car. That's an example of what this equation is referring to. Now we've studied collisions through this scope. There's also an equivalent way of describing the physics of a collision. So rather than simply focusing on the distance that a force acts over, we can look at the amount of time that a force acts. They're very similar. That relationship is called the impulse and change in momentum theorem. So we know that force during a collision is determined by Newton's second law. A refresher, Newton's second law is net force equals mass times acceleration. Force equals ma. Acceleration is a change in velocity over a change in time. So if we substitute acceleration into this equation, we get force equals mass times change in velocity over time. So let's think. We have some object that has mass. If that object also has velocity, it has momentum. So we see momentum right here in this equation. Mass times velocity. If this velocity is changing, then that means this object's momentum is changing. When velocity changes, momentum changes. Mass is going to stay constant if we're talking about the same object. So we have some mass with a changing velocity or changing momentum over time. Now, if we were to isolate the momentum portion of the equation by taking time and putting it over here, multiplying it by both sides, canceling out this side, we get this equation here. Now this is a force exerted over some time to cause a change in momentum. We call this the impulse momentum equation or impulse momentum theorem. Now, impulse is the force multiplied by the time. That's when you quantifiably, that's how you would describe that. Qualitatively, you can think of it as impulse is the change in momentum. So this is your impulse here. F times t is impulse. Impulse is equal to a change in momentum. Just as in our last example, work was equal to a change in kinetic energy. But work itself is force times distance. Now, what this brings us is this. A small force exerted over a large period of time produces the same impulse as a large force over a short period of time. So impulse is equal to your change in momentum. Those will be constant. Meaning momentum can be created or destroyed. It's going to be a constant throughout. But what fluctuates is your force exerted over the time at which that force is exerted. We'll talk more about that now. So let's look at an example. Say we have you. You are a person, you're 50 kilograms. You're going to do two experiments. You're going to land on a soft grass surface and you're going to land on concrete. You already know which one's going to feel better. Let's talk about why in terms of physics. So the concrete. Let's assume that as we're falling to the ground, we have a velocity of 3 meters per second. And when we hit the ground on impact, our velocity changes. It changes from 3 meters per second to 0 when we stop. Now, for that change in velocity, we know we're going to have a change in momentum. When we change velocity, you change momentum because momentum is mass times velocity. So a change in momentum equals mass times a change in velocity. If we write this out, we have our change in momentum equal to our mass times our change in velocity. We went from, well, it's v final minus v initial. So our final velocity was 0 meters per second minus our initial, which was 3 meters per second, gives us Negative 3 times 50, which gives our change in momentum is equal to negative 150 kilograms times meters per second. As the last board said, a change in momentum is equal to the impulse. So your impulse is negative 50 kilograms times meters per second. Now, if we think about the impulse momentum theorem here, it's force times the change in time is equal to the change in momentum. Let's say our change in time, meaning when I hit that concrete, the amount of time that my body was in contact with that concrete during the collision before the concrete restored itself back to equilibrium, when it bent just a little bit, say my body was in contact with that concrete for 0.5 seconds. That is my change in time here. If I put that in here, I know that F times so a force exerted on my body from the concrete over 0.5 seconds is equal to my change in momentum. Another way of thinking about this is a force exerted on your body over 0.5 seconds will change your momentum by this amount. Taking that relationship and solving for the force, that concrete would exert 300 newtons on my body. It's negative because it's the concrete exerting on me now. It's going this way, up towards me. I'm hitting it. Concrete has to exert 300 newtons of force over 0.5 seconds to change my momentum by this amount. So that's the concrete. Let's look at the grass. The grass has the same change in velocity, meaning my body is still falling at the same rate. I'm going to hit the grass in the same way. So I'm going from 3 meters per second to 0. The grass will stop me. So my change in momentum is also the same at negative 150 kilograms times meters per second. That's what the last board was saying. No matter what the scenario is, your change in momentum will be the same if your initial conditions are the same. If you're starting at some velocity and then going to the same final velocity, your change in momentum will be the same. Thus, your impulse will be the same. What varies from surface to surface is your force, the force exerted to stop you, or the force exerted to change your momentum, and the time at which that force is being applied. So here we are with the impulse and momentum theorem. So force exerted over some time frame will change your momentum. Let's say this time frame is now 1.5 seconds, because we know grass is much softer. Grass will give a little more than concrete. Thus, it's going to allow your body to be in contact with that surface for more time. It's going to give under you, causing a longer duration of time that force is being applied to you, which we'll see lessens the force applied to you. So force exerted for 1.5 seconds in order to change your momentum by the same amount, 150 kilograms times meters per second, you solve for force, you get 100 newtons. So the grass exerts 100 newtons on your body to have the same change in momentum, whereas the concrete exerts 300 newtons on your body to have that same change in momentum. So it's the surface, and it's the amount of time your body's in contact with that surface that determines the force exerted on your body. So now we have these two theorems, the work energy theorem here, and the impulse momentum theorem there, both describing how we can describe collisions in terms of physics. Which one you use depends on the situation. If it's easier to use this one here, depending on distance. So the force is decreased on your body, or in a collision, when the distance over which that force is applied is greater. The force over here decreases when the time frame is over a longer period of time. So which one you use is up to you. Now if we look at the conservation of momentum, or conserving momentum, look at two graphs here. When I have no cushion, so I just hit something, boom, no cushion, kind of like the concrete example, I have a great force over a short period of time. Now let's say, same collision happens, except I put a cushion there now. I have a small force over a longer period of time. The area under the graph is the same for both scenarios. The area under the graph represents the change in momentum and the change and the impulse. So now, The change in momentum is identical, but the impact force is very different due to the difference in duration of collisions. This is the take-home message. So gentlemen, take notes on the impulse momentum theorem. Be ready to apply this theorem towards your car build and towards our chapter challenge. And keep the essentials in mind.